Hello and welcome. I'm Nitin Sethi from Nainital, India. I have 3 years of experience building various deep learning applications. In this tutorial, we'll be building an image in painting and a super resolution tool, and for that we'll be using Keras, which is a high level deep learning framework. So the sessions will go like this. First of all, we'll be learning about the basics of Keras so that we get a basic sense of how do things work in Keras. Then we'll be learning about the basics of inpainting, that will include the architecture, the model architecture, and what all losses do we use in our inpainting. Then after that we'll be coding our inpainting, where we'll be writing the code for our generator, discriminator, and we'll be training it, and in the end we'll be saving a model which we'll be using in the end for our tool. Then we'll be learning about the super resolution basics, like what is the architecture of super resolution, what all losses are being used in the super resolution, etc. Then we'll be coding the super resolution. It will include everything from building generators to building discriminators to loading data to saving our models to training and everything. In the end, we'll be using both the models that we trained, like the super resolution and the inpainting one, and we'll be building a tool that will be taking an input from command prompt. It will be taking the image location from the command prompt, and it will be taking whether the tool wants inpainting or super resolution, and it will be applying that function, whichever command we give, it will be applying that function and doing that super resolution or inpainting task. That's it. I hope you enjoy watching the videos as much as I enjoyed creating it. All the best. Welcome back. So in this video, we'll be learning the basics of Keras. We'll be doing that through a classification problem, that is, we'll be classifying MNIST dataset. MNIST dataset is the hello world of machine learning, of deep learning. So I'll just show you it once. So it has a training set of 60,000 examples and a test set of 10,000 examples. It has numbers from 0 to 9 in it. So you can see here, this is the hello world of machine learning, Keras. We'll be doing that using Keras, which is a high level framework used for deep learning. In that, we can use TensorFlow, CNTK or Theano as the backend. We'll be using TensorFlow as our backend. So let's start on our problem. What we'll be doing is we'll be building a very basic neural network to learn about the various layers, how does exactly neural network work, etc. So first of all, we'll import the required dependencies. Keras. So first of all, we'll import the required dependencies. So we'll import numpy as np. Then we'll be importing matplotlib. Matplotlib is used for visualization purpose. Now from Keras we'll be importing the dependencies. So, and one more thing, you should try to always change runtime to GPU. So go to runtime, change runtime type, and here you should change to GPU for faster processing. So first of all, we'll import Keras. Then from Keras.datasets, we'll import MNIST. So Keras has even a few more datasets, toy datasets that you can use. So I'll just show you once. So Keras has Sifartan dataset, which is a dataset over 10 categories and 50,000 test and 50,000 train and 10,000 test images. Keras has Sifa 100 dataset, IMDb movie review sentiment classification dataset, Reuters Newswire topic classification MNIST, and fashion MNIST dataset, which is used to classify various t-shirts, trousers, pullovers, etc. It also has a posting house price dataset, which has various house features and the price of that house. So you can use these datasets for your own task. For example, when various research papers are released, most of them try implementing their research paper on these datasets. So because they define the benchmark. So you can try playing around with the datasets. So after that, we'll be importing sequential from keras.models import sequential. So in Keras, you can make your models in two ways. One is sequential and the other is functional. In functional, all the layers are used as functions, while in sequential, you can add one layer over the other. The difference between sequential and function in terms of usage is, in sequential, you need to have just one input and one output. You cannot build multi input or multi output models using sequential, while in functional you can build multi input or multi output models in a functional. So here we'll be, since we are at a beginning stage, we are using sequential. Then we'll be importing the various layers which are pre-built in Keras. So from keras.layers import dense, we'll be importing dense layer. We'll be importing activation. We'll be importing conv 2D and max pooling 2D. So these are the layers that we'll be importing. So I'll just show you the layers also in Keras. Okay, never mind. So dense is the most basic form of layer. Activation is used to add an activation function, for example relu, prelu, etc. Conv 2D is a convolutional 2D layer, and max pooling is used to perform max pooling function. So I'll just show you once. Conv 2D. So in this you can learn how does a conv 2D work. So suppose this is an image and this is a conv 2D filter. So what we'll do is we'll pass a filter over this image. For example, first of all it will be over this, and a number will be generated. I'll tell you how the number is generated. Then we'll pass that filter over these numbers, then over these numbers, then we'll come one step down, this and this. So after a filter of 3 by 3, this will generate a 3 by 3 image. So how does it work? The conv filters will have certain values. So when we are passing this filter over this, so this value will be multiplied by this, this by this, this by this by this, and so on, and all the values would be added together. Similarly, after these, we'll pass the filter over these, and this one value would be multiplied by this by this, and so on, and we'll add all those values. So this is how a convolutional neural network layer works. So in a model, these numbers, what exactly these numbers will be, they are learned during the training process itself. So this is a convolutional layer. During max pooling, what we do is we take the average, we take the maximum value of this, then we take the max value of this, etc. Like if it is average pooling, then we take the average value. So this is how max pooling and conv2d layers work. So after that, we need to import one more thing, that is categorical, that will be used for classification. I'll tell you later, like how does it work. So from Keras .utils .numpy underscore utils, we'll import to underscore categorical So once we have imported all these, we are ready to start building. So first of all, we load our data. So the data is already present in MIST. We just need to load it. So we load it by xtrain, xtest. So it should be xtrain and ytrain. Xtest, ytest. So this is the training data and this is the test data. In that, this is x, this is y, this is x, this is y, equals to MNIST dot. So use load underscore data, and the data will be loaded. It will take a little time to download that data. Yeah, it has downloaded. So let's see the shape of our data. X underscore train dot shape. So the shape is 60,000, 28, 28. That means there are 60,000 training examples, and each image is 28 by 28. The size of each image is 28 by 28. Let's see of ytrain. So that should be like the number of training examples. I think it's 10,000 and 28, 28. Ytrain dot, xtrain xtest dot shape. Yeah, so it's 10,000, 28, 28. So this is the number of examples, training examples or test examples, and then it is the size of image. Then we'll see the shape of ytrain. So this is 60,000, that means 60,000, and then it will be the category, and the shape of ytest, it will be 10,000, yeah. So it is the number of training examples, So let's see xtest once. So this is, there are various ytrain. Let's see that. So as you can see, there are various numbers. They represent from 0 to 9, which exactly is the number. So now, once we have learned a little about data, now we need to reshape this data. Usually, deep learning algorithms accept data in the form of number of training examples, comma the height, comma the width, and the number of channels. So since this is not an RGB image, the number of channels is just one. So we need to reshape our data into that particular shape, that is the number of training examples, height, width, comma 1, because 1 is the channel here. So xtrain will be xtrain dot reshape xtrain dot shape 0, comma xtrain dot shape 1, comma xtrain dot shape 2, comma 1. So this will reshape our training data. Similarly, we'll also reshape our test data. So xtest will be xtest dot reshape xtest dot shape 0, so now we'll check the shape. So xtest dot shape, as you can see, it has been successfully reshaped. So it's number of training examples, height, width of image, and 1, that is the number of channels here. Now, as you saw before, our Y train is numbers, but we need to convert it into one hot encoding. And what exactly is one hot encoding? So for example, here suppose we have 0 to 9, 1, 2, 3, 4, 5, 6, 7, 8, 9. So what we do is, we have a total of 9 numbers. So what we do to represent each, we write 9 zeros, sorry 10 zeros, because there are 10 classes. So it's 3, 6, 7, 8, 9, 10. And similarly, and so on. So what we'll do is, we'll replace the 0 by 1. For 1 we'll replace the first. For this we'll replace this by 1, 1, and so on. So 0 will be represented in our data as this, 1 will be represented as this, 2 will be represented as this. So this is called one hot encoding. So we need to one hot encode all our train and test Y. So for that, Keras provides us a pre-built function which is to underscore categorical, the one that we imported here, this one. It converts data into categorical data. So we'll be using that now. So now it has successfully converted our data into categorical data. So let's once check it once by train dot shape. So it's 60,000 comma 10. Why? Because there are 10 classes 0 to 9 and y train 0. So this is y train 0, that means 0, 1, 2, 3, 4, 5. That means the first image is number 5. So this is how all our images are represented now in y. Okay, did we import Keras? Okay. So now we'll start making a function. For that we'll be making a sequential function. So we do that by model equals to sequential. After that we'll start adding various layers over that. So we do that by model dot add. So this is how we add layer, and now we'll tell which exactly layer do we want to add. So first of all we'll add a conv 2D layer. So once you've defined shape, we'll tell it like how many filters we want. So we'll be giving 50 filters. Then we need to tell it the kernel size. Then we need to tell it the strides. Then we need to tell it padding, whether the padding means whether the size of final image will be same as initial or will it be different. So we are putting it as same. After that we'll be adding an activation function which is relu. Then we'll be adding a max pool 2D layer. We'll give it a pool size of 2, 2. Then we'll be flattening the layer. After flattening, we'll be adding a dense layer. Then in the end, we'll be adding a softmax layer. And since we want to classify it into 10, so we'll be giving 10. So this is the layer that will be performing the actual classification task. Okay, so we need to import the flatten layer also. So our model is, we've defined a model. So let's see a summary of a model once. So this is how we see the summary of our model. So our model has a total of 491,060 parameters and all of them are trainable. So these are the layers that we've defined and these will be the output shapes. So once we have done this, now it's time to compile a model. So before compiling, first of all, we need to define an optimizer for our model. So here we'll be defining an Adam optimizer. Opt will be equal to Keras dot optimizers dot Adam, and we'll give a learning rate of 0.001. So Keras provides us various optimizers, so you can check here. It provides us stochastic, Adagrad, Adadelta, Adam, Adamax, Nadam, these according to our need. So once you've defined our optimizer, it's time to compile a model. So we do that by model dot compile. First of all, we need to define a loss. So we'll define a categorical cross entropy loss. So these are the various losses that can be defined: mean squared error, mean absolute error, squared hinge, categorical hinge, log cosh, cosine proximity, etc. So we are using categorical cross entropy because this is a categorical problem and we need to classify it. So optimizer, we'll be giving the one that we just defined, and we'll giving it matrix equals to. So matrix is never used during our training part. It is just used to show the results, like how good is the accuracy coming, though it's not used. Categorical. So now once we are done with this, it's time to finally train a model, the thing that we are all waiting for. So we do that by history equals to model dot fit. We'll give it our train data, which is x train comma y train. Then we'll define the batch size, like how many we want to be processed in one batch. I'll be giving it as 64. Then we'll be defining a validation split or epochs, etc. So we'll be defining epochs as 10. Okay, I don't want it to train for very long because this is just to show you. So I'm giving it just 3 epochs. Then we'll also be required to give it a validation split. So we'll give it as 0.2. In the end, we can give verbose equals to 0. So now it will start training. Okay, never mind, let it train. So after that, to predict the results, what you do is results model.evaluate. What it does is it evaluates our data, like how well has it done, and we give it our test data, x underscore test, y underscore test. So this will evaluate our data, and in the end we'll be printing the results, that is the test accuracy, like how accurately did it work on our test data set. So using test accuracy and training accuracy, we'll know that if a model is overfitting, underfitting, or it's working perfectly. So results 1. So that will give us the test accuracy. It will take some time because I'm not using GPU for now. So ideally you should change runtime type to GPU and it will work. It should be very fast. I'm like training some other model. So this is how we use Keras to make a basic classifier. So in this we learned how to load data, we learned basics about sequential model, we learned about two categorical function, we learned about various layers, we learned a little about the loss that we gave, optimizer, etc. Hello and welcome back. So in this video, we'll go over the architecture as per the research paper of Image Inpainting. So the overall architecture of this model is a simple encoder and a decoder pipeline. So you have an encoder at the beginning and a decoder then. What the encoder does is it takes the input image with missing regions and it produces a feature representation of that image. So what the encoder does is it downsamples that image to produce a feature representation, and the decoder that takes this feature representation and then it produces the missing image content. So it is very important to connect encoder and decoder through a channel wise fully connected layer. That means all the pixels in last layer of encoder should be connected with all the pixels of first layer of decoder. This is required so that all the information, even the information which is far off, transfers very well, because if we connect encoder and a decoder by just convolutional layer, it will transfer just the local information. So our encoder is derived from AlexNet architecture. So even if we have an input image of 227 into 227, we'll use the first 5 convolutional layers, and after that we have pooling layer that will give us a feature abstract of 6 into 6 into 256 dimensional feature representation. So, but in contrast to AlexNet, our model is not trained for ImageNet classification. Rather, the network is trained for context prediction from scratch. So, what the problem is, like if we take all the 6 into 256 and convert that into a fully connected layer, that would give 9216 parameters. So, if we have 9216 parameters in encoder last layer, we also need the same number in decoder first layer. So that will produce over 100 million parameters, which are very inefficient to train. So to elevate this issue, to overcome this issue of 100 million parameters, what we do is we use a channel wise fully connected layer, and we use that to connect encoder features to decoder, and we'll describe that in the next slide. So what channel wise fully connected layer is? This layer is a fully connected layer with groups, and each group is intended to propagate information with activations of each feature map. So if the input layer it has m feature maps of size n cross n, this layer will output m feature maps of dimension n cross n. So what this does is, if there are like if so now the number of parameters is just mn to the power 4, otherwise it would have been m square n to the power 4. So by this we reduce the number of parameters. Now we'll talk about decoder. The decoder, what it does is it generates pixels of image using encoder features. So the encoder features are connected to decoder features using channel wise fully connected layer that we discussed in the last slide. The channel-wise fully connected layer is followed by 5 up-convolutional layers. So what up-convolutional layer does is it upsamples the image, that is increases the size of image with learned features, and we use ReLU activation function. So it can be understood as upsampling, like I said, followed by convolution or convolution with fractional stride. The intuition behind is straightforward, that the series of upconvolutionals and nonlinearities produce a nonlinear weight upsampling so that we can easily reach our original target size. So this was the architecture of image in painting. Welcome back. So now we'll go over the losses for image in painting. So the context encoder needs to understand both the entire image, that is the content of the entire image, as well as produce a possible hypothesis for the missing part. This is a hard task because it needs to fill in both the missing areas where it cannot get hints from nearby pixels, and this also requires a very deep understanding of the scene. It should know like what exactly is the scene, what should be here, so it needs to understand the entire image also, and the ability to synthesize high level features over large spatial extents. So a model needs to understand both the content of image as well as produce hypothesis of missing part, as I told just now. This is multimodal task because there can multiple ways of filling the missing region. So missing region can be filled in multiple ways. So what we do is we solve this problem with we decouple this burden in a loss function. We use two losses simultaneously. One is to minimize reconstruction loss and other is for adversarial loss. So what happens is the reconstruction loss, that is we use L2 loss, it captures the overall structure of missing region in relation to context. So what it does is it produces multiple outputs, while it forces it to produce the reconstruction loss forces the model to produce output such that all the image features, all the overall context is kept into account. And what adversarial loss is the GAN loss or the generator loss. What it does is it picks a particular mode from that distribution. So what it does is it says that of those various that reconstruction loss has calculated, one should be specific. So that is used using only the reconstruction loss. Whenever we use just the reconstruction loss, a blurry prediction is predicted, while when we add adversarial loss, that results in a sharper prediction. So that was it about our losses for our image in painting. Hello and welcome back. So now we'll start coding our image in painting. So we'll be coding in Google Colab. As you can see, I've opened a collaboratory. It's very easy to open. Like if you want to open, just go to collab.research.google.com and like you can directly open. The advantage of using Colab, or the reason we are using Colab, is it offers free GPU usage. So we'll be able to leverage that for our project. So what you need to do is, first of all, new Python 3 notebook. So it will open a new Python 3 notebook. Just give it a minute, it's loading. So Colab has been like recently released by Google a few months back, like less than 2 months back. So first of all, what we'll do is we'll import our required dependencies. So I'll change the subject first of all, image in painting. So we'll be importing our required dependencies. Import. Let me see if it's visible properly. Yeah. Required dependencies. Increase the size. I suppose it should be visible better now. Yeah, it's visible better. So we'll be using Keras, which is the high level framework, and we'll be using TensorFlow as a backend. So first of all, we'll be importing a print function and division from future import print function and division. Then we'll be using, as I said, we'll be using Keras. So first of all, we'll be importing the dataset. So we'll be using CIFAR 10 dataset. CIFAR 10 dataset is a dataset that splits into 10 different classes. I'll just show you that dataset. So what it does is, it's a very famous dataset. So what it does is, it's a dataset with 6,000 images per class, and it splits into these 10 classes. So there are a total of about 60,000 images, out of which 50,000 are training images and 10,000 are test images. So the classes are airplane, automobile, bird, cat, deer, dog, frog, horse, ship and truck. So we'll be using this dataset for our training process. So first, Keras has already pre-built that in it. So we'll be importing that from keras.datasets import CIFAR 10. Then we'll be importing all the layers which will be required. So we'll be doing from keras.layers import. So first of all, we'll need batch normalization. What batch normalization does is, it prevents the, I'll just show you once, I think that will be better. It subtracts the mean and divides by standard deviation. So as you can see, first of all we'll divide by mean, and then we'll subtract mean and then divide by standard deviation. So this is what batch normalization does. Batch normalization. Then we'll be importing the activation layer. These are the various activation. This is used to give various activations like ReLU, leaky ReLU, etc. or sigmoid. Then we'll be importing our usual dense layer. Then we'll be importing input layer, which is used to take inputs. And dense is the most basic form of our neural net layer. Then we'll be importing reshape, which is used to reshape. Then flatten. It converts a layer which is in the form of image into a flattened, which can be used by dense. So a con 2D layer, if we want to put dense layer after a con 2D layer, we'll use flatten first to flatten the layer, and only then we can put our dense. Then we'll be using dropout. Then we'll be using multiply. Then Gaussian noise. We also need to import embedding. And then zero padding. So these are all the layers that we need to import. So once we import layers, yeah, and we also need to import max pooling 2D. Max pooling 2D. We need to import activation. So we'll not be using ReLU. We'll be using leaky ReLU here. It is like as said by the author of this image in painting paper that leaky relu works better in this case. So we'll be using that from layers dot advanced activations. Then we also need to import our upsampling 2D layer. So we'll do that by from Keras dot layers dot convolutional import upsampling 2D. And have we imported a conv 2D layer? No, so we'll also be importing a conv 2D layer. Then we need to import our optimizer, which we'll be using Adam from Keras dot optimizers import Adam. Then we also need to import sequential and model. So we'll be doing that by from Keras dot models import sequential and model. Then we need to import our losses from Keras import losses. After that we need to import to categorical, which converts into category from that is present in keras.utils import to categorical. And then we'll be importing a backend import keras.backend as k. So I think we are done importing all the Keras layers. So next we need to import a matplotlib, which is used for data visualization. Import matplotlib dot pyplot as plt. And then we'll be importing numpy. Yeah, another thing I wanted to tell you is, like, suppose we want to use GPU. So I'll just show you how do we actually use our GPU. You go to runtime, change runtime type, and here select GPU. As you can see, it also has, we can also use TPU. So I'll select GPU and then I'll save. So now we'll start using our GPU. So I'll run this. So as you can see, it's initializing, it's connected, and like it's GPU here. No module name layers. Okay. From Keras.advanced activation. Is it? Let me check. Leaky relu. Keras.layers.leaky relu. This looks fine. Okay, from Keras dot layers dot, yeah. Okay, so now we have imported. So now what we'll be using, we'll be making a class and we'll be calling that context encoder. So we'll be writing all our functions in that particular class. So class context encoder. First of all, I'll write a init function. So first of all, we'll be defining our normal variables like our number of rows in our image, number of columns, our mask height, our mask width, channels, number of classes, etc. So we do that by self.image rows. So these are the number of rows in the image, 32. Self.image columns equals to 32. Self.mask height equals to 8. Self.mask width equals to 8. So the channels will be 3. Usually in most of the images, channels are either 3 or 1. That if it's an RGB image, the channels will be 3. If it's like black and white, then the channels will be 1. Then self.num classes. So num classes will be used by Discriminator to tell whether the image is real or fake. So we only have two classes, which is real and fake. So I have written num classes equals to 2. Then we need to define the shape of our image. Image self.image underscore shape. So this will be self.image rows, comma self.image columns, and self.channels. Then we'll be telling the missing image, self.missing image equals to self.mask height, self.mask width, and self.channels. After that, we'll be defining a optimizer. So we'll be using Atom optimizer. So we have already imported our optimizer. We just need to call it here. So we do that by optimizer equals to Atom, and we'll give a learning rate of 0.0002 and 0.5. So once we have done this, now it's time to build and compile our discriminator. So what we are doing is, first of all, we'll build and compile our discriminator, and then later we'll write the function for our discriminator. Build and compile our discriminator. So we do that by self dot discriminator equals to self dot build underscore. So what we need to do is we need to make this function which is build discriminator. So we'll be making it later, build underscore discriminator. After that we also need to compile it. So we do that by self.discriminator.compile. And for compiling, the loss we'll be using is binary cross entropy. Why binary cross entropy? Because our discriminator is a it classifies into two different classes. So that means we'll be using a binary cross entropy, and the two classes are whether the image is real or the image is fake. Binary cross entropy. The optimizer we'll be using the one that we have already defined. Optimizer. And then the metrics that we'll be using will be accuracy. So once we have worked with our discriminator, now what we need to do is we need to build a generator. So we'll repeat the same process, build the generator. So we'll be doing the same thing, self.generator equals to self.build underscore generator, and remember later that we need to code that also. So I'll just write it down here. So we need to code this. This I'm just writing to remember. To code build discriminator, and now we are calling generator also. So we need to code these two things. Generate, okay. Self dot generator equals to self dot build underscore generator. Now what the generator will do is the generator will take noise as input and it will generate the missing part of our image. Generator will take noise as input and then generate the missing part of our image. So first we need to take that. So masked underscore image equals to input shape equals to self dot image underscore shape. So what this masked underscore image is doing, we are taking input which is of the size of our image, and I've written the variable as masked image because the image that we are taking as input, that will have a mask. That means it will have some of the surface as white. That means that is the thing that we need to inpaint. And then we'll be doing gen underscore missing equals to self dot generator. So we'll be sending a masked image into generator and we'll get this. Now for the combined model, we need to train only the generator, not the discriminator. For combined model, we need to train just the generator. We need to train just the generator. So what I'll be doing is I'll be setting our discriminator as non-trainable. So we do that by self.discriminator.trainable equals to false. So now we have set our combined model. In the combined model, we have set our discriminator as false. So now the discriminator will take the generated image, like the image that generator generated, which is gen underscore missing. So that will be our input to a discriminator. So what we did was, first of all, we took our image which we wanted to inpaint. We gave that as our input to our generator, and then this will go, this gen underscore missing will go as an input to a discriminator. So we do that by valid equals to self dot discriminator gen underscore missing. So what the purpose of, what the role of discriminator will be? To tell if it's real or fake. So this discriminator is taking generated images from generator as input, and it will output whether the image is real or fake. It will output whether the image is real or fake. So now we need to define a combined model. Okay, wait. Combined model. So we do that by self.combine will be equal to model. It will take as input a masked image, and the output that it will give will be valid. And we also want to get our output as gen underscore missing. Why also? Because valid will be the result, which is like whether it's real or fake, but actual generated image is gen underscore missing. So we want that also. That is like more crucial, I'll say. Now we need to compile this. We do that by self.combine dot compile. In that we'll give our loss as mean squared error and binary cross entropy. So mean squared error will tell us like how much the image matches our real image, and this binary cross entropy will tell us like whether the image is real or fake. Then we'll give weights to the loss. Weights will tell us how much of importance we are giving to loss. So we'll be giving 0.999 and 0.001. So these weights are the same as the author used. The author experimented with different weights and he found like these two work quite well, and the optimizer that we'll be giving will be optimizer. Yeah, so now we are done with like most of the things. First of all, we imported our required dependencies. Then what we did was defined our various variables that we'll be using, that is the image size, the mask size, the optimizer, etc. Then we built our discriminator and compiled it with binary cross entropy. Then we built our generator and compiled it. No, sorry. Then we built our combined model and then we compiled that combined model, and the discriminator we put it as non-trainable. So that is it. In the next video, we'll learn how we'll be working on this build underscore discriminator that we left for coding. So we'll be learning how to build our discriminator. Welcome back. So now we'll code a generator, that is we'll build a generator. So we'll do that by def build underscore generator, and it will take as input self. So first of all, we'll be making a sequential model. We do that by model equals to sequential. Now we'll start adding layers. So first of all, we'll be adding a conv 2D layer. Model.add conv 2D, and we'll giving 32, and the kernel size will be 3, and the number of strides that we would be giving is 2, and the input shape for this will be the shape of the image, self dot image underscore shape, and padding will be same. So once we add this conv 2D layer, then we'll be using our adding leaky relu. So I'll just show you how is leaky relu different from relu function. I think you'll be able to better understand with a graph. So what relu does is it takes maximum of 0 or so its graph is either, if it's negative it's 0, otherwise it's the number itself. While what leaky relu does is it takes maximum of this and this, so its graph is not 0 here. So this is the graph of leaky relu. So the authors, when they were experimenting, they found that leaky relu is working far better than just the relu function. So we'll be using that. So model.add leaky relu, and alpha will be 0.2. Then we'll be adding batch normalization. Model.add batch normalization. The momentum will be 0.8. Now we'll be adding another conv 2D layer. Conv 2D this time 64. Kernel size will be 3. Strides will be 2. The padding will be same. We'll be adding leaky relu again. Model dot add leaky relu. The alpha that we'll be giving will be same, that is 0.2. Then we'll be adding our batch normalization. Model dot add batch normalization, and the momentum will be 0.8. So we have added conf2d leaky relu batch normalization, then conf2d leaky relu batch normalization. Then again we'll add the same set, that is conf2d leaky relu batch normalization. Model dot add conf2d this time we'll be giving 128. The kernel size will be 3. The strides will be 2, and the padding will be same. Then we'll be adding leaky relu. With alpha equals to 0.2, and then a batch normalization. Model dot add batch normalization, and the momentum will be 0.8. Then again we'll be adding, but this time we'll be giving a dropout. Model dot add conf2d (512). Kernel size will be 3, 1. Strides will be 2, and the padding will be same. Then we'll be adding leaky relu again. Now we'll be adding our dropout. We are adding dropout to avoid overfitting, and we'll be giving it as 0.5. So this one was the encoder part of our generator. I'll just mention here encoder. Now we'll be making the decoder part of our generator. So now we'll start upsampling the image. Upsampling means increasing the size of our image. Model dot add upsampling. (2D). Then we'll be giving a conf2d layer. 128. Kernel size will be 3. The padding will be same. Now we'll be giving a activation. So this time we'll be using relu activation. Model.add activation, and the activation is relu. Now we'll be adding our batch normalization again. Model.add batch normalization. The momentum will be 0.8. Then we'll do the same part again. We'll upsample, we'll add con2d, then relu, then up and batch normalization. Yeah, we'll do the same thing again. Upsampling, con2d, relu, batch normalization. And after that we'll be adding another con2d layer, and then we'll apply our TANH activation. Model.add upsampling 2d, model.add conf2d, and this time we'll be giving 64. The kernel size will be 3. And the padding will be same. Then we'll be giving our activation relu. Then we'll be adding a batch normalization again. So we did upsampling, con2d, relu, batch normalization. Upsampling, con2d, activation, and batch normalization. And the momentum will be 0.8. Now we'll be adding a con2d layer. Model.add conf2d. So this time we'll be giving self.channels, and kernel size will be 3, and the padding will be same. Now you'll ask, why are we giving self.channels? So here self.channels is 3 because this is after that we'll be adding just TANH layer, but this is the last layer that can actually change the size or the number of channels of that image, and this is also the last layer of our generator, as you can see. So what this last layer is doing, it's creating our image. After it's creating our image, so we need to make sure that it has 3 channels. So these are the same as they were before. So once we have done this, now we'll add a TANH function, TANH activation, model.add The authors found that this activation worked quite well in this case. Manage. Then we'll write model dot summary. This will show the summary of the model. And now masked image will be input self dot image underscore shape. So here we are taking the input whose size is image shape, and this input is the one that we need to the image that we need to inpaint, and the output of the generator will be scope missing equals to model masked underscore. This will be the output of our image. So this is our input image, and this will be our output image. Output image. So once we have done this, then we'll return a model. We do that by return model, and we'll give inputs and outputs. So the input is masked image and the output is generator missing. So this is how we code a generator. So in the next video we'll be learning how to code a discriminator. So to revise, first of all we added con2d, relu, batch normalization. We did the same thing 4 times, so that was our encoder part. But in here we added dropout to avoid overfitting. Then we added the decoder part where we were upsampling this image. Upsampling means suppose the image initial size is 12, 12, 3. So what upsampling will do is it will make the size twice. It will do as 24, 24, 3. So similarly, like if size was like 50, 51, the size will become 100, 101. So this is what upsampling does. Then con2d relu, then same upsampling con2d relu, and then batch normalization, and in the end this is our output, and we added the activation as tanh, and then we returned our model. So this is our generator model. Hello and welcome back. So now we'll be coding a discriminator. So first of all, we coded a generator in the last video. So let's start our coding. So we'll be done with this once we code a discriminator. Build discriminator, and it will get self as input. So first of all, we'll define a model that will be sequential. Then now we'll start adding layers. So first of all, we'll be adding a conf2d layer. So we do that by model dot add conf2d 64. Kernel size will be 3. Strides will be 2. Input shape will be self dot missing shape, and then the padding will be same. Once we add a conf2d layer, we'll be adding leaky relu. Model dot add leaky relu alpha will be 0.2. Then we'll be adding a batch normalization. Model dot add batch normalization, and we'll be giving momentum as 0.8. Then we'll be adding con2d leaky relu batch normalization once again. Model dot add conf2d. This time we'll be giving 128. Kernel size will be 3, strides will be 2, and then the padding will be same. Kernel size strides equals to 2, and then the padding will be same. Now we'll be adding leaky relu as a activation again. Model dot add now we'll be adding batch normalization. Momentum will be 0.8. So we added con2d leaky relu batch normalization. Then again we added the same group con2d leaky relu batch normalization. Now we'll be adding the same group again, and then we'll be flattening the image. So model dot add conf2d. This time we'll be giving 256 and kernel size will be 3. Kernel size will be 3. Padding will be same. Now we'll be adding a leaky relu again with the same alpha, and then we'll be adding a batch normalization. Model dot add leaky relu alpha will be 0.2, and then batch normalization. Batch normalization. The momentum that we'll be giving is 0.8. Now we'll be using the flatten layer that will flatten it, because after that we need to add a dense function for our classification, which will classify into two parts, that is whether the image is real or whether the image is fake. So for that we need to flatten the image first. Model dot add flatten. So once our image is flattened, we'll be adding a dense layer again, and we'll be giving activation as sigmoid. Why sigmoid? Because we want to classify it into two parts, like 0 or 1, whether the image is fake or whether the image is real. So model dot add dense 1 comma activation equals to sigmoid. Sigmoid. So once we have done this, we'll do model dot summary. This will show us the summary of the model. Now we need to take inputs before we send this model back. So we do that by image equals to input. The shape will be self dot missing shape, and validity means whether the image is real or fake. That will be model of image. So this model will be getting image and the output will be validity. In the end we'll return our model. So we do that by return model, and the input will be image and the output will be validity. So this is the way we code our discriminator. So now we have coded our generator and we have coded our discriminator. First of all, we imported dependencies. We gave these normal inputs like default values or whatever. We compiled a combined model and we combined our discriminator. Then we made our generator. Then we built our discriminator. So in the next video, what we'll do is, as I told you before, we'll be using CIFAR10 dataset. So in the next video, what we'll do is we'll write a function that will randomly put dots. I mean, because for image in painting, we need parts of image to be missing. So that function will randomly remove parts of the images. So we'll learn that how to do that in the next video. Welcome back. So now we'll make a function that will make a random masks on our image. So I'll show you by an example. For example, suppose we have an image of nature. Suppose we have this image. So what our function will do, our function will select a random point in that image and our function will put mask on that image. So what that mask will be exactly, that mask will be nothing but a white spot on that image. So what our image in painting's task is, we'll be feeding this image with white spot on that, and our generator has to predict what exactly has to be there in that white place. Though we won't be doing on this, we are doing on a CIFAR10 dataset. So now, since we cannot manually work on all the 50,000 images, we cannot draw masks, so we'll be making a function that will do that for us. So that will solve our problem of making masks. So let's start writing our code. Mask underscore random. It will get images. First of all, we need to decide at what point we want to create mask. So we'll do y1 equals to numpy.random.randint. So whichever point, this is the y, so there will be 4 points in our image, which will be y1 x1 y2 x2. So first of all, we need to decide which point we need to randomly decide a y1 point. So which exact location will that be? That will lie between 0 and the height of image minus the height of mask. For example, I'll just show you again nature. Suppose we have this image, we want the height of our mask to be this much. So our point y1 will lie between this and this, because above this there will be the point. Or if we look from top, a point will lie from here to here, because the rest part will have a mask. So now we'll need to choose a random point between 0 and self dot image underscore rows, but from that we need to subtract a mask height, self dot mask underscore height. So now what will y2 be? Okay, wait, we also need to decide like how many we need. So we need images dot shape 0. So as you know that images are fed in the neural network in the form of the number of training examples, then the height, the width, and then the number of channels. So 0 contains the number of training examples or the number of images. So we need masks of for these many images between 0 and this. So we have defined our y1. Now we'll define our y2. Our y2 will be equal to y1 plus self dot mask underscore height. Now we'll like we have decided y1, we'll also need x1. So for x1 we'll do the same, but instead we'll do here image underscore rows minus width, not the height, numpy dot random dot randint 0 self dot image underscore rows minus self dot mask underscore width. And how many do we need? Same as this, like the number of training examples. So the number of training examples we have is stored in images dot shape 0, images dot shape 0. So we got y1, y2, we got x1. Now we need x2. So that will be similar to y2, x1 plus self dot mask underscore width instead of height. Now we have decided where all the mask will be. The next thing we need to do is we need to actually add our masks. First of all, we'll make mask images equals to numpy dot empty like images. So it will make a numpy array that will be same as images, and so it will be empty, so that it will contain a masked images. Next, what we'll do is we'll also store our missing parts. Missing parts equals to numpy dot empty. So images dot shape 0. This will tell how many for how many images or for how many training examples do we need parts. Then self dot mask underscore height. So this is the height of our mask. And then self dot mask underscore width. So this will be the width of our mask. So for example, suppose you are making a suppose you are missing this, you are adding a white part here. So what will it be? I mean, how will you store it? You'll store, first of all, you'll store the number of training examples, that is on for the number of images you are adding it on. Then if you want to store this, you'll add height, width, and the number of channels. So that's what we have done. We have added height, width, and we need to add channels. So we do that by self dot channels. So these two will store our masked images and our missing parts. So now we need to actually add it. Oh, just let me bring it up here. So we do that by we'll loop over all our images. So we do that by for I comma image in enumerate images okay. So masked underscore images will be image dot copy. So this will have masked underscore images will have the entire image now, later, or now only, just a few minutes later now we'll be adding masks. So first of all we have copied the image. Now we need the 4 points, so where we'll be adding masks. So we do that by y1, y2, x1 and x2. So the 4 points will be y1 of I, comma y2 of I, comma x1 of I, comma x2 of I. So these are the points or the coordinates of our mask. So first of all, let's store our missing parts. That is this missing underscore parts equals to missing underscore parts for ith image will be equal to masked image, these coordinates of masked image. So we do that by masked image underscore y1 comma underscore y2. That means from y1 to y2 and from x1 to x2. So this has a missing part. For example, suppose we were adding mask here, so this will now store this part. So now let's actually add a mask. Masked image so what we'll do is on this part, that is on this part we'll give the value as 0. So that will add a mask. So we do that by masked image colon y1 y2 comma x1 x2 comma colon. Okay, we need to add a colon here also because we also need to give channels that will be equal to 0. So now we have told it like this value inside it should be 0. So we are like almost done, and then masked images I will be masked image. So we are done. This will add a mask. Now we need to, in the end, return our masked images and our missing parts. So return masked images, missing parts, and let's also return our coordinates or our points, y1, y2, x1 and x2. So now we have defined our initial values, we built our generator, we built our discriminator, we built a function to add masks. So the next thing in the next video, what we'll be learning is how to actually train our model, because that is like, training is very important. I already told you like how to use GPU this way. So I'll just save it. So in the next video, we'll be learning how to train our model. Hello and welcome back. So now we'll make a function for the training part of our image in painting. So let's start coding. So this will get self epochs, that is for the number of epochs that we want to run it. The batch size, what will be the batch size for this, and sample interval. Sample interval will decide like after how many epochs do we want to save our function or generate our image. So first of all, we need to load our data set. So as I told before, we'll be using Cifart and dataset. So we'll load our dataset by x underscore train comma y underscore train comma. So that is for training and this is for test. Since we don't need test, we are actually throwing it. This means we are not storing it anywhere. We are instead throwing it away. Now let's load our dataset. Cifar 10 dot load underscore dataset. So this loads our data. Load the dataset. Now we won't be training on all the dataset. What we'll be doing is we'll be taking out two classes and we'll be training on that. So let's take out dogs and cats classes and then we'll train on that. So we do that by x underscore cats equals to x underscore train where y underscore train equals to 3 dot flatten. Similarly, x underscore dogs will be almost the same. Instead of 3, we'll give it as 5. X underscore train y underscore train equals, where this equals to 5 dot flatten. Now after that we'll be stacking this one over the other. So we do that by using numpy.vstack function. So we'll be doing x underscore train equals to numpy dot vstack, and what do we want to stack? X underscore cats and x underscore dogs. So once we have done this, now we need to rescale it. So currently our data is between 0 and 2 to 5. We want to rescale it between -1 and +1. So what we'll do, we'll divide both by 2 to 5 by 2. So 2 to 5 by 2 is 255 by 2. Since our data is between 255 and 2. Yeah, so our data is between 255 and 0. So 255 by 2 is 127.5. So what we'll do, we'll divide both of these by 127.5. So that will give us our data between 0 and 2. Then we'll subtract 1 from both the sides. So that will make our data between -1 and +1. So this is how we'll convert our data into -1 to 1. We'll rescale between these. Rescale between -1 to 1. As I just told, x underscore train equals to x underscore train. First we'll divide by 2 to 7.5. Sorry, 1 to 7.5. That is, we'll divide by half of this, and then we'll subtract 1 minus. So now our data is between -1 and +1. Why? Because 0 after being divided by 127.5 remains 0, and 255 after being divided by 127.5 it converted into 2. After we subtracted 1 from both, so 0 minus 1 will be -1 and 2 minus 1 will be 1. So this is how our data got converted. Now once we have rescaled it between these two, so what we'll do is we need to reshape y. So we do that by y underscore train equals to y underscore train dot reshape -1, 1. Now once we have done this, we'll make two classes which will be like our ground truths. One will depict that all of the images are real, and the other will depict that all of the images are fake. So what we'll be doing is we'll be feeding those as a result of our training process. So we do that by adversarial ground truths. We do that by valid equals to numpy dot ones batch size, 1, and fake will be numpy dot zeros batch size comma 1. So this means the images are real and this means the images are fake. So once we have done this, we'll loop over for epoch in range. So we want to run it for epoch times. So for these many times we got it before. I'll just delete this now because this isn't required, I suppose. So first of all, we'll train our discriminator. Train discriminator. So for that, we'll randomly select a batch of images. So we do that by idx equals to numpy.random.randint. So what we want to do is we want to select the number of images that we want to select as batch size, and all those images will be between 0 and the number of images in our data set. So we are choosing random integers between 0 and x underscore train dot shape 0. That is, we are choosing numbers randomly between 0 and the total images we have, and how many of these we want batch size number of them. So these are the IDs. So the images will be x underscore train of IDs. So once we are done with this, we need to mask our images. What does masking images mean? Like we wrote the function before, which was mask underscore random. What it returned was mask images and missing parts and y1, y2, x1 and x2. So we'll be using that function now. So now you will get a more sense of like why did we do that. So masked underscore images comma missing parts comma, we don't need anything else, so we'll just throw equals to self dot mask underscore random self and images. Okay, mask underscore random and we need to give it images. So this will produce masked images which we'll be feeding to in our training loop. So now we'll be using our generator to produce images. So gen underscore missing will be self dot generator dot predict and we'll send masked images. I'm sorry. So after this we'll get this will be the result of our generator. Now we need to train our discriminator. And what we'll be training our discriminator over this gen missing. So when we give this gen missing, we'll say that our discriminator should output that the image is fake, and when we give our original image, that is this images, our discriminator should, or when we give this missing parts, our discriminator should output that our image is real. So we do that by train the discriminator so this is the loss when the images are real. So self dot discriminator dot train on batch missing parts comma valid. So here we are telling that we need to give these all images and all these images are real. So this is our X and this is our Y. So we are training over that. So after that we need to train over fake images, telling the discriminator that these images are fake. So self.discriminator train on batch gen underscore missing. This gen underscore missing is the output of generator, so it is actually fake, so we are giving it fake. So here we gave it the numpy array of zeros, that means it is fake. So now our total loss will be 0.5 into numpy dot add d underscore loss underscore real comma d underscore loss underscore fake. So you'll ask, why have I done 0.5? That is because we want to take average of the losses. We could have done like d loss real plus d loss fake upon 2, so that is like same. Instead of dividing by 2, we are just multiplying by 0.5. So after this we need to train our generator. So we'll be training our generator when our discriminator is frozen. So that is like we'll be training our entire model. So we'll be running over our combined model, but since discriminator is frozen, so in actual only the generator will be trained. So G loss will be equal to, this will be equal to self dot combine dot, now we'll be training on our batch again, but we are training on combined model. Self dot combine dot train on batch masked images and we need to give missing parts and valid. So what we have actually done, what we have given these masked images, so these will be given, and missing parts and valid means they are original. We want it to be trained in such a way that the generator should be trained in such a way that, so our discriminator is outputting that these masked images. So we are training in such a way that since our discriminator is fixed, so our generator will change its W's and B's change its parameters in such a way that it has to prove it will make the image in such a way that the output of generator is real image. So once we have done this, we'll plot our losses. Plot losses. So we'll be doing that by print %d loss colon %f comma, and accuracy will be percentage dot 2f percentage. So this will be for our discriminator. Now for generator it will be GLOSS %f comma, mean squared error will be %f, and now we'll be giving all of these. So epoch number, d loss 0, that is the loss, accuracy, so we need to multiply it by 100, d loss 1, g loss, and then the mean square error will be z loss 1. So here it had to be g loss 0. So this will print all this will print our losses for all the epochs. So after that we'll also like to see results. So but we don't want to see results for all the epochs. We want to see results after a certain number of epochs. So we'll be using the sample interval that we got, which is 50. So after every this sample interval, we want to see our generated images. So we'll do that by if epoch percentage sample interval equals to 0, idx equals to numpy dot random dot randint 0 comma x underscore train dot shape 0. So we are doing similar thing that we did before. We are selecting 6 images randomly, or 6 images randomly from our training set. So images will be x underscore train idx self dot sample underscore images. So we need to make a new function which will sample our images, epoch and images. So now we have done this. This entire process will train both our generator and our discriminator. So in the next video we'll be learning we'll be actually coding this sample underscore images function, which will take a few images from our training set, and it will actually depict like what exactly is being done. So we'll be doing this. So till now we imported all our dependencies, then we started our function, we gave some inputs, which is like optimizers, and defined our optimizers, compiled our models, etc. Then we built our generator, then we built our discriminator, then we built mask underscore random, which was randomly putting masks on our images. Now we wrote our train function, which will actually be training. So after this, we'll be writing sample underscore images function. Welcome back. So now we'll be writing a sample images function, which will be loading the images, taking it through the generator, and then saving them. So let's start coding. Sample underscore images self epoch, that is the which epoch are we currently in, and the images. So rows and columns will be 3 and 6. So first of all, we need masked images, missing parts, etc. So we'll be using that mask randomly function. This function, we'll be calling this function. Okay, I just saw that this is not aligned properly. So we need to align this also. So let's use that function mask underscore randomly. So it was returning masked images, missing parts, and x1 y1 y2 x1 x2. So masked images, missing parts, and y1 y2 x1 x2. This will be equal to self dot mask underscore randomly images. So now we'll be using our generator to predict. So gen underscore predict will be equal to self dot generator dot predict masked images. So this will produce our predictions over masked images. So after that, this is between -1 and 1. So this is between -1 and 1. To plot it, we want to convert it between 0 and 1. So what we'll be doing is we'll be multiplying both sides by 0.5. So multiplying both sides by 0.5 will convert it into -0.5 and 0.5. Then we'll be adding 0.5 to both. So that will make it between 0 and 1. So this is how we'll be converting it into 0, 1. So we do that by images equals to 0.5 into images plus 0.5. Similarly, masked images will be equal to 0.5 into masked images plus 0.5, and gen underscore missing will be equal to 0.5 into gen underscore missing plus 0.5. Now we'll be plotting, so we do that by comma axis equals to plt dot subplots row comma column. Now we'll be looping over all C for I in range C. Axis 0 comma I dot im show images I comma colon. So in the first row we'll be showing images, that is what it means. In the second row we'll be showing our masked images. And now we don't need our axis, so what we'll do, axis 0 comma I dot axis will be turned off. Similarly, axis 1 comma I dot im show masked images axis, we'll turn off axis here also, dot axis will be turned off. Now we need our filled images, so we haven't created them yet, so we'll be doing that by filled underscore m equals to images I dot copy filled underscore images y1 of I 2 y2 of I comma x1 of I to x2 of I comma colon, that means all channels will be gen underscore missing of I. Now we'll be showing this also, axis 2 comma I dot im show filled underscore im two comma I dot axis will be turned off. So once we have done this, now we need to actually save our image. So we do that by plt dot save fig, tlt dot save fig images backslash %d dot png, or you can also save it as jpg if you want to. Epoch OC. So it will be saved in images folder, and the name will be the number of epoch that is currently running, 5th, 6th, 10th or whatever, dot png, and after that we'll close tlt dot close. So now we have written the function which will save our images. So now this should work fine. Like once you send this images, it will run and it will save those images. Now we also need to save our model. What you'll observe that we haven't written save model function anywhere yet. So in the next video we'll be learning how to save our model. Further, I'll tell you, if you press this, you'll see a table of contents, code snippets and files, which of files are there. If you go to files, you'll observe that if you're using Collab, by default this images folder won't be there. So what you need to do, you need to press this mkdir images and then run. So what this will do is, this will make this folder available. That means it will create a new folder that is called images. So currently it's showing cannot create directory because I was testing something and I've already created it. Though if you run it for the first time, you'll be able to successfully create it. So I'll just show you with some other name. Make their images 2. So as you can see, it ran fine and it would have created a folder called images 2. So since we are saving all our images in images folder, so you need to make their images to create this folder, otherwise it will show an error. So that was it for this video. In the next video we learn how to save a model. So I'll just save it once. Hello and welcome back. So now we'll be learning how to save a model. So we'll be writing a function to save a model. Def save underscore model self Okay, so everything is well aligned. So we need to save both our we'll be saving both our generator and our discriminator. So what I'll be doing is, I'll be making a function in this also, def save model. This will get the model and the model name, like with what name do we want to save our model. So this means which model do we want to save, discriminator, generator, etc., and by what name do we want to save. So model path will be saved underscore model backslash %s dot JSON percentage model name. And we also need to save weights. So weights path will be saved underscore model backslash percentage s underscore weights dot hdf5 percentage model name. Then options will be equal to file architecture, file arc, model path, comma, file weight, weights path. After that, the JSON string will be equal to model dot to underscore JSON then open options, file architecture, comma w dot write JSON string model dot save underscore weights options file weight. So this entire function will save a model, but now so we'll be calling this function. We need to save both a generator and a discriminator. So save underscore generator, and we'll save it by generator. Next, we also need to save our discriminator. So we do that by save self dot discriminator, comma discriminator. So this is how we save a model. So this will save both our generators and our discriminators one by one, and the generator will be saved by name generator. And remember that both of these models will be saved in this directory, which is saved underscore model. So we also need to create this directory first. We do that by mkdir saved underscore model. So just run this and it will create this directory in your Google Colab. So this is how we create a model. So in this video, so now we have like completed this. First of all, we defined our image size, rows, compiled a model, etc. Then we built our generator, then we built our discriminator, then we on random images we built masks, then we started training, then we wrote function for saving our images. Now we wrote for saving our model. So in next video we'll be actually training a model. We'll be actually using whatever class we have done till now in our actual function. Hello and welcome back. So now we'll be actually running a function. So for that, first of all, we need to write if name is main Then we need to call that function context encoder will be equal to context coder, and now we need to decide like for how many epochs we want to run, what will be the sample interval, what will be the batch size, etc. So we do that by context encoder. We'll call the train function because we want to train context encoder dot train. So we need to decide for how many epochs we want to train. So we'll be training for 25,000 epochs. The batch size will be 64. The sample interval, that is for how many after how many intervals will it be saving images, will be let's do it 1000 because we don't want a very large number. So it will save like 25 images, so that should be fine, I suppose. So after doing this, first of all we need to check if we, before running this, we need to check if we have required folders, etc. So go to files, refresh this. So as you can see, we don't have a few folders. So as I told you, we need two folders. One is saved underscore model, which will have a model saved, and the other function will be, check, there was one move I remember. Okay, one is for saving models and I think other is for saving images. So that is images. So we need to create these two folders, images and saved underscore model. So we'll do that. Make directory images and make directory saved underscore model, right? Saved underscore model. So as you can see, once we refresh, we have these two folders, which is images and saved model. So after that, you'll see one more thing. We are saving images, but we haven't written any function to save our model. So we'll write that also. If epoch so we are running it for 25,000 epochs. So what I'll do is epoch equals to 24,900 self dot save underscore model. Yeah, so this is done. I think we have all the required settings fine. So let's run this now. I'll remove this because we have already created those files. So one more thing that you need to make sure that you are like set up on a GPU, because running this on CPU will be like very heavy, and I don't think it will take like very long. It won't be possible. So if you have a GPU which has a CUDA in your system, then it's very good. Otherwise you should use Collab. So make sure that you change the runtime to GPU. I have already set it to GPU. So now we'll start running. So this ran fine. Let's try running this. Okay, model dot add invalid syntax. Okay, let me check. 60 activation relu. Okay, those two are opening. Okay, I think there should be one more. Okay, so it ran fine. Now we'll run this. It will take like quite long. And it takes 0 positional argument, but 1 was given. Okay. Okay, let me try this. Okay, I think I got it. Yeah, that worked fine. Has no attribute, missing shape. Is it? Okay, missing image it should be. Where is it? Image. Okay, let's try running this now. Model dot add missing shape in build discriminator. Okay. Missing image and miss image shape. Okay, this will be image shape only because we are giving it to generator. So we need to give image shape. To discriminator, we'll be giving missing image. So let's check that. Missing image. So let's try running this now. Yeah, so I think it's working. Not fine. There's no attribute missing shape. Okay. Okay, we have self dot missing underscore image attribute, build discriminator, self dot missing image, missing image. Okay. Okay. Missing image. In build discriminator input में input shape. What's happening? Image equals to input self dot input shape and discriminator. We already have input shape. Oh, sorry, self dot missing image it will be. Okay, Keras dot datasets dot Sephartin no attribute load underscore dataset. How is that possible? There is an attribute load underscore dataset. Sephartin dot load underscore data. Okay, it's not dataset, it's load underscore data. Load underscore data. Okay, so I suppose it's running now. Okay, so it's downloading data, which is Sephartin dataset. So it will take like 36 seconds to download that data. So since we made it into a class and we compiled it all in one go, that is the reason like we found all the issues together. Okay, so cefarten.load underscore data. Okay, so this is a data set of 50,000 32 into 32 color training images over 10 categories. Okay, what's this now? Okay, okay. Masked images, mask underscore random. Empty takes at most 3 arguments. Shape, mask height, mask width. No, that is missing parts equals to. Okay, let's check that. Self dot mask underscore random. Okay, missing parts. This takes at most 4 arguments. Okay, let me see. Numpy dot empty. Numpy dot empty. Shape and dtype float. This should be fine. Yeah. So let's do one thing. Oops. Shape equals to masked underscore image is not defined. Really? Okay, it's masked underscore images. Okay, we need to do this. Yeah, this should work fine now. Error when checking expected to have shape. Array with shape 33. Is it? Gen missing will have self.generator.predict. Masked images. Okay, masked image will be numpy image.copy. Okay, so image will be copied here. So we need this. So missing parts will be masked image. This, okay, this is fine. So masked image y1 y2 will be equal to 0. Masked images, this one should work, I think. And masked images will be masked image. And okay, so missing parts, we have defined it. This is perfect, this is perfect, this is perfect. So masked image, yeah, this looks fine. What was the issue? Okay, so masked images, I've shaped it, but got shape 33. Okay, I don't think there should be an issue here. Okay, the issue is we need to write dot copy here. Yeah, I think it should work now. Okay, so now we'll run again. It had to be equals to. So I hope it works this time. The images will be saved in images folder. and the model will be saved in saved underscore model folder. Okay, so looks like, okay, it's downloading the data. So it has also given us the summary of the so this is our discriminator and this is our generator, or is it a combined model? Yeah. So this is our generator and the above is the summary of our discriminator. So our generator has a total of 826,435 parameters and our discriminator has a total of 373,633 parameters. Okay, it has downloaded the data and as you can see that now it's working fine. It is giving us the discriminator losses and the generator losses. After every 1000 intervals, it will also save images. So it has run a total of these many intervals. So let's see it running till 1000 intervals so that we can like at least see a few images that at least see one image that it has created. Okay, so it ran for 1000 intervals. Let's refresh this and look in images folder. Okay, so as you can see there are two images, one is for 0th epoch and the other is for 1000th epoch. Let's open this 0th epoch. So as you can see, this is like the training is negligible because it's not able to, it's just giving random blot here. Now let's check the same for 1000. So it hasn't like, it's not perfect, but yeah, it is like at least better. For example, here it's able to identify that the color has to be somewhat like this. Even here it's able to identify, okay, the color has to be somewhat like this. It's far better than 0th one. So let's train it till 30,000, 25,000. So after 25,000, I think we should be able to identify and I think it should work well. Hello and welcome back. So in this video, we'll talk about the architecture of super resolution. So super resolution has a generator network. As you can see, these are the initial layer. First of all, there is an input layer. Then the initial layer has a kernel size of 9. It has a stride of 1 and then the number of feature maps as 64. After that, we have a prelu activation function. Then we have various residual blocks with skip connections. Then we have convolutional network, batch normalization, and this is element wise sum. I'll tell you like what element wise sum is. So here k means kernel size, like kernel size is 3. N means the number of feature maps, that is 64 here, and S means the number of strides. After that we have a convolution. and a pixel wise shuffle and then a p-relu, and in the end we have an output. So these are residual blocks. So what happens is, for example, like you can see this is connected here. So what will happen is the output of this batch normalization and the output of p-relu would be added here. So this preserves information. For example, when the activations would have passed through all these layers and it would have reached here, some information might have been lost. So this adding ensures these skip connections ensure that the information is preserved. So there are various skip connections from here to here, from here to here. That is, after every residual block there is a skip connection. This is one residual block, this is second, this is third, fourth and fifth. Each residual block has a convolutional layer, then a batch normalization, then p-relu activation function, then again a convolution, batch normalization, and element wise sum. That is the sum of the output of this batch normalization and the output which was before convolution, that is here this one. So this is the architecture of generator network. Similarly, for discriminator network, we get an input, then there is here in discriminator network we are using a leaky relu function. In generator we were using a p-relu function, activation function. So it has a convolution layer, a batch normalization, and then a leaky relu. Then there are various sets of different layers, like first of all convolution, batch normalization, leaky relu. Then this is repeated multiple times. Then in the end there's a dense layer with 1024 feature maps, then a leaky relu function, then a dense layer of 1, and then a sigmoid function which tells whether the image is real or fake. So this was the super resolution architecture. Welcome back. So in this video we'll be discussing about the loss that we have used in our super resolution. So super resolution has a perpetual loss function, that is, it has two losses. One is the content loss and the other is an adversarial loss. So each has a multiplier. For content loss it's 1, and for adversarial loss it's 10 raised to the power minus 3. So the definition of a perceptual network is critical for performance. Like this is very important for performance. Usually it is based on mean squared error, but we have improved it further by adding both the content loss and the adversarial loss. So in the next slide we'll discuss individually what the content loss is and what the adversarial loss is. The content loss. So instead of like in other architectures, it is a mean squared error is usually used as content loss, but here we have not used mean squared error. Instead what we have used is we have taken a VGG19 pre-trained network, and we have taken a certain layer of that VGG19, and the activation of that is the output of that layer. We have used that as the Euclidean distance between feature representation of reconstructed image and reference image. For example, suppose we have a reference image, we pass it through our VGG network and output it at a certain layer. We do the same for reconstructed layer, then we get feature maps for both of them, and we take Euclidean distance between them. So that is the content loss that we have taken. For adversarial loss, in addition to content loss, adversarial loss is the generative component of our GAN. That is, this is the loss which comes after this is the adversarial loss. That is, it is the one that like we were adding a sigmoid layer which will define in the discriminator, which was telling whether the image is real or fake. So the loss from that is the one which is the adversarial loss. So adding both of them, adversarial loss and generator loss, makes sure that the output looks real and it has a content that matches, that resembles a lot to the real image. So that was our loss for our super resolution. Hello and welcome back. So now we'll be working on super resolution. super resolution. So first of all, we'll be making a data loader class. The function of that class will be to import our data and convert it into required format. So for super resolution, what the class would be returning is the images. So for super resolution, the class would be picking up images from a particular folder or we can either load our own dataset. For example, here we'll be loading our own CIFAR 10 dataset which Keras already provides. You can also load data from a particular folder. After that, we'll be doing some pre-processing on that data, and in the end we'll be returning both the low resolution and the high resolution data. So let's start coding. So first of all, we'll import SciPy. Then we'll be importing glob. Then we'll be importing NumPy as NumPy. Then we'll be importing matplotlib.pyplot. Matplotlib.pyplot. We'll be importing that as PLT. And in the end, we'll be importing CIFAR 10 dataset, which is present in Keras.dataset. So now we'll start coding our data loader class. So first of all, we'll be making the init function. Self. So this will be the name. What name do we want to give to our dataset? And the image resolution. So self dot dataset name will be dataset name, and self dot image resolution will be image underscore res. Now we'll be making a function which will actually be loading the data. So I'm writing this is testing. So if it's true, that means the data is test data. So I'm writing as false by default because the data by default won't be test data. So now let's load our data. So x comma y comma. So this dash means you want to throw the data. We are not storing here anything. We are just storing our training data. We don't need test data. Even though I think we don't need y here, though I'm still storing. So you can even enter underscore here also because we don't need that. So we'll be loading our data from CIFAR 10 dot load underscore data. So CIFAR 10 is a dataset with I think about 50,000 images in training and 10,000 in test. It is divided into 10 different classes. I'll just show you. So these are all the different classes. This is 32 into 32 color images with 6,000 images per class. Yeah, so it's 5,000 training, 50,000 training and 10,000 test images. So we'll be using that. So data type will be train, but it will be train only if uh, is testing equals to false. If is testing is true, then it won't be train, then it would be test. So we write that by equals to train. If not, is testing, else test. So that means it will be test if is testing equals to true, otherwise it will be false, otherwise it would be train. So now we'll be randomly selecting images from our Spartan dataset. So we do that by batch underscore images equals to numpy.random.choice. So what we are actually doing is, I'll just show you once. So I'll just show you with an example. This I'm showing you just to like explain you what we are doing. So what we will be doing is, the shape of x will be 50,000, 28, 28, 3. That is the number of training examples, the height of image, the width of image, and the number of channels. So what we will be doing is, we will be randomly selecting different training examples from the range, and we need to select the batch size number of training examples. For example, if the batch size is 5, then we need to select 5 training examples. So we select by numpy. We will be using numpy.random.choice function. So we are doing that numpy.random.choice. So the range will be x.shape 0 and size will be batch size. That means we have selected batch size number of images and we have randomly selected from our batch. So I'll just show you once. So x.shape is, like I said, 50,000, 32, 32, 3. So x.shape 0 will be 50,000. So I'll just show you what does this mean, numpy.random.choice. This means we are randomly selecting Okay, did I not import numpy? Okay, I'll import numpy. Import numpy as np. I'll just delete this. I'm just doing this to show you once. Oops. I'll just do it 5 for now. So as you can see, from 50,000 it has randomly selected 5 integers. So that's what we'll be doing here. So once we've selected random images for our batch, then we'll be making 2 images underscore high resolution and images underscore low resolution. Now for image path in batch images. So that means for image, I should write image index, I suppose. That will be like, so batch images has like different indexes of image. For example, from 0 to 50,000. So we are looping over each index. Then image will be equal to x of image underscore index comma colon comma colon comma colon. So that means, like, suppose batch images is Suppose batch images is 5, 6, 7, 123. So for first time image index will be 5. So image will be equals to x 5 comma colon comma colon. That means we have selected the actually the sixth training example because it starts from 0. So once we have selected the training example, then height comma width will be self dot image underscore res, and low height comma width will be integer of h by 4 and integer of w by 4. Now we'll be resizing our images. We'll be resizing this image into high resolution and low resolution. So we do that by image high resolution equals to scipy dot misc dot imresize image comma self dot image resolution. Then we also need low resolution images. Scipy dot misc dot imresize image comma self dot image comma low height low width. So if we are training, we'll also randomly flip images right left, so that will like actually increase the number of training examples. So we do that by if not is testing and numpy dot random is less than 0.5, only then image high resolution equals to numpy dot flip lr. So what numpy dot flip lr does is it flips right left image. Similarly, we'll also be flipping low resolution images. Image underscore low resolution. So once we have done this, we'll be finally appending that image in our images underscore hr, these two images underscore hr dot append image underscore hr and images underscore lr dot append image underscore lr So after this, what we'll be doing is we'll be converting that image from -1 to 1. So I'll just show you. So currently the image is between 0 and 255. 0 and 255. So how do we convert it into -1 and 1? Like I told in my other video also, what we do is we divide by half of 255. So half of 255 is 127.5. Yeah. So we divide both sides by 127.5. So it will be 0 to 2. Then we will subtract 1 from both sides. So it will convert from 1 to -1 to 1. So we'll apply that here also. Images underscore high resolution will be numpy dot array images high resolution upon 127.5 minus 1 point. Similarly, we'll also be doing with low resolution images. So we'll be doing that by images underscore low resolution equals to numpy.array images underscore low resolution upon 127.5 minus 1 point. And in the end, we'll be returning both our high resolution and low resolution images. So return images high resolution, comma, images low resolution. And then we'll run this. Okay, from my import matplotlib.py.splt batch images equals to so in this video we made a data loader class. So in the next video we'll be actually moving towards our next part, where we'll be making a class for our super resolution GAN. So now after this we'll be successfully able to load our data. After loading, we have randomly selected a few, or the batch size number of images. We have resized them according to our low resolution and high resolution. We have flipped those images, and then we have appended those function in images underscore high resolution and low resolution. What we have also done is we have converted those into the form -1 to 1, and then we have returned. Welcome back. So now we'll be moving on to make our super resolution class. So let's start coding now. Like in the last video we coded data and loader. Now let's start coding the next part. So first of all, we'll need to import the required dependencies. So we'll do that. I'll just increase the size a bit if it's like better. So from future, we'll import print function and division. Then we'll be importing scipy. Then from Keras.layers, we'll be importing various layers. So we'll be importing batch normalization. We'll be importing the input layer. We'll be importing the dense layer. We'll be importing reshape. We'll be importing flatten. We'll import dropout. We'll import concatenate. Then we'll be importing activation. We need to import zero padding 2D. Then we'll be importing add conv 2D, and we'll be importing upsampling. So that is the advantage of using libraries like Keras. Imagine if you had to like code from scratch all these, it would have been like too long and too tough. Then we'll be importing prelu and leaky relu from keras.layers.advanced activation. Import p r prelu and leaky relu. Then we'll be importing VGG19 model. That is available in Keras.applications, a pre-trained model. Import VGG19. After that, from Keras.models, we'll be importing sequential and model. Then we'll be importing our optimizer. We'll be using Atom optimizer. Then we'll be importing datetime. Then we'll be importing matplotlib.pyplot. We'll be importing that as PLT. So after this, we need to import sys, numpy and os. Import numpy as np. Import os. Import sys, and then we'll be importing keras.backend. As k. Keras.layers. Okay, I think it's advanced activations. Let's try that. Okay, so we've imported all the layers. So now we'll start making our super resolution class. Class super resolution GAN. So first of all, we'll be defining a init function. First of all, we'll be defining the input shape. So self.channels will be 3, the number of channels. After that, we need to give the height of low resolution image and the width of low resolution image. So height will be 64. And width will also be 64. So now we can define the shape of low resolution image, which will be self.channels, self.lr height and self.lr width with commas between them. So once we have defined the low resolution shape, now we'll be moving on to define the height, width and shape of high resolution image. So self.high resolution height will be self.low resolution height multiply by 4. Similarly, self dot high resolution width will be self dot low resolution width into 4. Now we can even define the shape of our high resolution image. That will be self dot high resolution height, self dot high resolution width, and self dot channels. So now we have defined the shape both of high resolution image and of low resolution image. So now we need to give the number of residual blocks that we want in our generator. Number of residual blocks in our generator. So we do that by self dot n underscore residual equals to 16 and residual blocks. Then we need to define our optimizer. So we have imported our Atom optimizer. We will be using that only. Optimizer will be Atom, and we'll be using a learning rate of 0.0002. This is like as per the author's recommendation. Like this one was the working best according to author. Now we'll be using the pre-trained VGG model that we imported before. We'll be using that to extract features from high resolution. We use pre-trained VGG19 model to extract features from the high resolution and the generated high resolution images, and we minimize the mean squared error between them. So self.vgg equals to self.build underscore vgg. So we'll be writing this build underscore vgg function later. What basically it will be doing is it will be like just building the vgg model and returning that. Once we have built the model, we'll set it as non-trainable. We'll set the trainability as false. Now we'll be compiling this model. We do that by self.vgg.compile. Loss will be mean squared error. Optimizer will be optimizer, and metrics will be accuracy. So once we have done this, what we'll be doing is we'll be configuring our data loader. Configure our data loader. So now we'll be using the actual data loader class that we wrote before in the previous video. So self dot dataset name. So we are using Cephart and dataset. So I'll just write Cephart dataset as our dataset name, and then self dot data loader will be data loader. The dataset name will be self dot dataset name. Image resolution will be self dot hr underscore height and self dot hr underscore width. So once we have done this, we'll be defining the number of filters in our generator and in our discriminator. We do that by self dot generator filters equals to 64, self dot discriminator filters equals to 64. Number of filters in the first layer of generator and discriminator. So once we have done this, now it's time to build and compile our discriminator. So we do that by self dot discriminator equals to self dot build underscore discriminator. So now we need to later write this build underscore discriminator also. What it will be mainly doing is it will be returning the discriminator model. Now we'll be compiling this. We do that by self dot discriminator dot compile. We'll be using loss as mean squared error. Optimizer is the one that we have already defined before, which was Adam optimizer, and metrics will be accuracy. So once we have done this, now we'll be moving on to build our generator. Build the generator. So now, like we used in build discriminator, build VGG, we'll be using a build generator also that we'll be coding later. So self dot generator will be self dot build underscore generator, where we'll be coding our build underscore generator later. So high resolution and low resolution images. We'll be taking inputs now. We do that by image underscore high resolution equals to input, and the shape will be self dot hr underscore shape that we defined before, which is here. Similarly, we'll be taking in low resolution images also, and we'll be defining this as our shape self dot high resolution shape. So once we have done this, now we'll be generating our actual high resolution version from low resolution images through our generator. So they'll actually be fake for now. Generate high resolution images from low resolution using our generator. So we do that by fake underscore high resolution, because they're actually fake, self dot generator, and we are giving our low resolution images. Now we'll be extracting the features from the generated image, this generated fake high resolution image. Extract VGG19 features of this image. So we do that by fake underscore features equals to self dot VGG fake underscore high resolution. So once we have done this, we'll say that in our combined model, we just want generator to be trainable. We don't want our discriminator to be trainable. In combined model, just generator should be trainable. So we are setting generator. So we are setting our discriminator as non-trainable. Discriminator as non-trainable. So we do that by self dot discriminator dot trainable equals to false. So now our discriminator is non-trainable. Now our discriminator will be determining the validity, whether the high resolution image is real or fake. So that will be discriminator will determine whether the high resolution image is real or fake. So we do that by validity equals to self dot discriminator and we are giving a fake high resolution images In the end, we'll make a combined model. So we do that by self.combine equals to model a combined model. So I forgot to mention here that we need to make a build generator also. So our combined model will have inputs as our image underscore low resolution and high resolution, and the outputs will be validity, that is whether the image is real or fake as per our discriminator and fake features. And in the end, we'll compile this model self dot combine dot compile. So the losses that we'll be giving is one binary cross entropy, and the other loss will be mean square error. We'll also be giving our loss weights, that means how important each loss is. So that will be 10 raised to the power minus 3 and 1. And our optimizer is the one that we have already defined before, which was Adam. So now we have compiled our model too. So in the next video, we'll be working on build VGG, where we'll be building the discriminator model. So in this video, we have defined a init function for our super resolution model class. Hello and welcome back. So now we'll start writing our first function, which is build VGG. It won't be very long because we'll just have to load our VGG model and then return the weights along with the weights. So let's start coding. So we do that by build underscore VGG self Now first of all, we load our VGG model. So this function builds a pre-trained VGG 19 model. That outputs image features extracted at the third block of the model. So first of all let's load the model, the pre-trained model VGG 19. Let me check if I have already imported it. Okay, so I've imported the model from Keras.applications import VGG 19, and now we are building. So we'll put weights as ImageNet. So now we need to set outputs to output of last convolutional layer in block 3. So we'll do that by vgg.outputs equals to vgg.layers, and that is the ninth layer, dot outputs, output. Set outputs to the output of last convolutional layer in block 3. So now we need to define our input. So we do that by image equals to input, and then we'll give it the shape. So the shape is self dot high resolution shape, and now we'll be extracting the image features from our VGG model. Extract image features. So we do that by image underscore features equals to VGG of the input that we gave, which is our image, and in the end we'll return our model. So our model will have inputs as image, like these are the inputs, and the outputs will be image underscore features. These will be the outputs. Image comma image underscore features. So this is how we write build VGG function. So in the next video we'll be learning how to build generator. So we have done this, and I'll just save it. Welcome back. So now we'll be writing the function that will build generator. So we'll be writing this function. So we do that by build underscore generator self. So first of all, in this we'll be like coding in two parts. First of all, we'll be defining the function which is the residual blocks, and then we'll be defining the decon2d block which will be used for upsampling, and in the end we'll be using those two functions to make our final build generator model. So let's start with defining a residual block. So we do that by def residual underscore block. It will get layer input and filters. So this is the residual block, and this is like same as the one that is described in the paper. So first of all, it has a conv2d layer. So we'll be doing that, we'll be giving that conv2d, and it will require filters, kernel size, strides will be 1, padding will be same, and this will be over layer underscore input. After this we'll need activation, which is relu activation. So relu activation means select 0 or max. Relu activation is the max of the number and 0. For example, if the output of this first layer, this layer is -5, then the output of ReLU activation will be 0. While if the output, like if output is less than output of this layer is less than 0, then the output of this layer will be 0. If the output of this layer is more than 0, then that will be the output. So the output of ReLU is 0 or max of the number. After this, we'll be giving a batch normalization with momentum as 0.8. After this, we'll be adding another con 2D layer. And the padding will be same. So same padding means the output of input layer and the output of same padding means the input will have the same size as the output. Now in the end, we'll be adding a input layer and the D, which is this output. So we do that by and in the end we'll be returning this D. So this is how we build a residual block. Now we'll be learning how to build a decon2D block, which will be used during upsampling. So this 2 will get layer input. First of all, we'll give upsampling. (2D). The size will be 2 and this will be over layer input. Then we'll be adding a con2D layer above this. And then we'll be adding activation, which is ReLU. And in the end, we'll be returning this layer. So now we are ready with residual block and deconv block. So here we added convolutional layer, ReLU, batch normalization, convolutional, and then added. So this was like we add the input, got this was the residual part, and in decon we upsampled, then con2D layer, and then activation ReLU. Now we need to start building a model. So first of all, we'll be taking input the low resolution image. low resolution image input image underscore low resolution will be input shape equals to self dot lr underscore shape. Now we'll be building a pre-residual block, that is the layers which are before our residual blocks. So this will be over image underscore lr that we just took as input, that is the low resolution input image, and then we'll apply our activation layer, which is relu. So now we have defined a pre-residual block, that is the layers before our residual layer. Now we'll be defining a residual blocks. R will be residual block C1, comma. So now we'll be looping over the number of residual blocks that we want. But we have already defined one residual block here, so we'll be subtracting one from this. Now once you've defined a residual block, we'll be defining a post residual block, that is the layers after the residual block. So first of all, we'll have a con2d layer. Now we'll be giving a batch normalization layer. Here momentum will be 0.8. And then we'll be adding now. Once we have done this, we'll be upsampling. We'll be using the decon2d function that we just defined. So once we have done this, now we'll be generating a high resolution output. So we'll be actually defining a conv2d layer for that. Conv2d. So once we have done this, now we'll be returning a model. Return. So what will the model be? The model will be image underscore low resolution, and the output will be generate the high resolution output, this one. So now we have defined a build generator function. So what it does is it takes in low resolution image from here and it outputs the high resolution image. So in the next video we'll be defining a, now we have already defined build generator here. In the next video we'll be defining a build discriminator function. So we have done this, so in the next video we'll be doing this. So now we'll start building our discriminator. Self. So like we did in generator, we'll also do in discriminator. But in discriminator, we'll define a D block or the discriminator layer. So now we are defining the block or the discriminator layer, which will get layer input, the filters, stride, and whether the batch normalization is true or not. That is whether we need to give batch normalization or we don't. So D equals to conv2d filters the strides will be strides and the padding will be same, and this will be over layer input. So after this, like in generator, we were using a relu function. In discriminator, we'll use a leaky relu function. So I'll just show you graph of leaky relu. So like relu was 0 or max, whichever is greater, max of 0 or the number. In leaky relu, it's ay or y. So the graph of leaky relu is like this. So we'll be using leaky relu as the activation here. Alpha will be 0.2. Now, if the batch normalization is true, that is, if in a particular layer we need batch normalization, then we'll define that batch normalization. So if the batch normalization had been false, it won't have gone inside this, and there would have been no batch normalization. And the momentum for batch normalization will be 0.8. And in the end we'll return D. So this is how we have defined discriminator layer. Now we'll start building a discriminator. So first of all, it will get an input image which will actually be higher resolution image. That was actually the image generated by either the generator, or when we'll give inputs as false, or otherwise the original image when we'll give them as true. Now we'll start defining the layers. So in the first layer we aren't giving a batch normalization. the strides will be equal to 2, d7 equals to d underscore block d6 comma self dot df into 8. So in the end, we'll be giving a dense layer. Then we'll be adding a leaky relu layer, or the leaky relu activation function, I'll say. And in the end, we'll be adding a dense layer with 1, and the activation will be sigmoid, because this will be identifying whether the image is original or it's fake. So we have made the model, or now we'll be finally joining our inputs and our outputs and returning that. So input was d0 and the output is validity. So we'll return a model with input as d0 and output as validity. So now we have defined our input model. We have defined our batch normalization model, which got input as high resolution, the shape of the high resolution image, and its output was a sigmoid function, that is, it will output whether the image is real or it's fake, or how real or how fake it is. So in the next video, we'll be writing the function which will actually be using the things that we have already built, which will be using the discriminator, generator and the init function and training it. So we'll be writing the train function. Welcome back. So now we have written a function which has defined a discriminator and a generator. So now it's time to finally write our train function. So we'll start coding that. So this train function will get self, the number of epochs, the batch size, the sample interval, that is after how much of interval will it save images. Datetime dot now. So now we'll be looping over the number of epoch for the range of epochs. So we do that by for epoch n range epochs. So first of all, we'll train our discriminator. So first of all, we need to load our images. So we'll be using our data loader that we wrote before. Uh, this one, data loader, this class, and load underscore data function. In that method, in that class, so images, high resolution, and images, low resolution will be equal to self dot data loader dot load underscore data, and we need batch size number of images to be loaded. So once we are done with this, we'll be converting our low resolution images into high resolution images using our generator. From low resolution image to high resolution version. So those will actually be fake images because they've been built by a generator. Now we'll be defining two numpys. One will be valid, that is numpy.ones, which will have all ones. That means that these images are original. And other will be for fake, which will be a numpy array of zeros, which will say like these images are fake. Valid equals to batch size, comma, plus self dot disk underscore batch, and fake will be a numpy array of zeros. Now we'll be training the discriminator. So we'll be taking out two losses. One will be for real images and the other will be for fake images. So for real it will be self dot discriminator dot train on batch the high resolution images and valid. That means we are telling the discriminator train that these are original images, and then we'll find a loss for our fake images. So here we'll be feeding a fake underscore hr and telling it that these are fake images. That is, we'll be giving the numpy array which is fake, which is a numpy array of zeros. Train on batch. So it will be fake underscore hr comma fake. That is our fake images, fake underscore hr comma fake. In the end, the final loss will be the mean or the average of both of them. So we'll add them and divide them by 2. So that will be d loss will be 0.5 into, so multiplying by 0.5 is same as dividing by 2. That will be 0.5 into numpy dot add d loss real and d loss fake. Once done with this, we will be training a generator. So for that, first of all, we need to load our sample images. Self.data loader dot load underscore data of batch size. Now generators want the discriminators to label the generated image as real. So we do that by valid equals to numpy dot once batch size comma plus self dot disk underscore batch. Now we need to extract the ground truth image features from our VGG19 model. So we do that by image underscore features equals to self.pgg.predict Now we'll be training our generators. So we'll actually be training on the combined model where the generator will actually be trained because the discriminator is frozen. train on batch so the inputs are image underscore LR, that is low resolution image, and images underscore HR, that is high resolution ones, and the output will be valid and image features. Then we'll note down the time. Date time dot now minus the start time. Now we'll plot our progress. Print. So we'll be printing the epoch and the time, that is how long did it take to run. Now if we are at save interval, we also want to save our generated samples, so we'll do that. If epoch percentage sample interval is 0, then it will self dot sample underscore images and epoch. So that is all. So now we have defined the function which will be used for our training part. So in the next video we'll be writing this function, which is sample underscore images. What it does is it saves our generated image. So our training is done. Our training is like the code we have written. Welcome back. So now we'll be writing a sample images function. So this one function we'll be writing. Sample underscore images So first of all, we'll be asking it to make directory if there is none. So we'll be doing os.make directory, and that will be images backslash percentages percentage self dot dataset name, and if it's exist okay, then true. Now we'll be defining the number of rows and columns. Those will be 2. Then we'll be loading a high resolution and low resolution images. We'll be using self.dataloader.load underscore data function. The batch size will be 2 and is testing will be true. Then the fake high resolution images will be the ones that are generated by our generator. Self.generator.predict low resolution images. Now we'll rescale these images between 0 and 1. Rescale from 0 to 1. So currently they are between -1 and 1. So what we'll be doing is we'll be multiplying both sides by 0.5. So that will make it into between minus 0.5 and plus 0.5. Then we'll be adding 0.5. That will make it between 0 and 1. So this is how we'll rescale our images. Images underscore low resolution equals to 0.5 into So we are doing it for all three, for our low resolution images, for our high resolution images, and for our fake high resolution images. Then we'll be saving the generated images and the high resolution original images. plt.subplots then for row in range R, for column comma image in enumerate fake underscore high resolution images underscore high resolution axis row comma column dot I am show image row we'll set our title as titles of column, and then we'll turn off the access. Then we'll save our image. Then we'll also be saving our low resolution images for comparison. For I, in range R, plt dot figure and then fig dot save fig images backslash percentages backslash percentage d underscore low resolution percentage d dot png. Self dot dataset name epoch I plt dot close. So now we have written the function that will actually be saving our images. So in the next video, we'll be writing the function that will save our model. Hello and welcome back. So now we'll be writing our last function, which will actually be saving our model. So we'll write that by save underscore model self model comma model name. First of all, we'll be giving it the model path that is equal to saved underscore model backslash percentages dot json percentage, the name of the model. Then we need to give it the weights path, weights underscore path will be equal to saved underscore model backslash percentages underscore weights dot hdf5 percentage model name. Now what you'll see is, if you look here, you'll observe that there is no folder called saved model. but we are saving it in saved model, so it will give an error. So what you need to do is you need to create a folder here called saved model. So how do you create that? What you need to do is exclamation mkdir, that is make directory, saved underscore model, and then run this. So now you need to refresh this. So what you'll observe that now there's a directory called saved underscore model. So our function will be able to save the models now. Then we'll make options equals to file underscore architecture model path, comma, file weight will be weights underscore path. Then JSON string will be equal to model dot to underscore JSON, then open options file architecture, that is we are opening the model path, comma w dot write JSON string. Then we'll save it, model dot save underscore weights, GHTS weights, options file underscore weight. So once we are done with this, we'll call this save function. We do that by save self dot generator, comma generator, and we'll also save our discriminator. So we do that by self dot discriminator and discriminator. So this is how we'll save our model. So in the next video, what we'll do is we'll actually be running this function to see how does it work, and we'll start our training process. Welcome back. So now we'll start training our model. So we do that by if name equals to name, then gan equals to, we'll make a gan, then gan dot train. Then here we'll define for how many epochs we want to train. For example, let's train for 100 epochs, though we are required to train for a very large number of epochs. The batch size will be 1 and the sample interval, so let's keep the sample interval as 10. In the end, we need to save our gan, so we write gan dot save underscore model. So let's run this. So we'll have to run others also. So let me first check like if I have the GPU enabled. Okay, the GPU is not enabled, so I'll enable the GPU once. So now the GPU is enabled. So let's run this again then. So now I'll start training. So it's downloading the weights of the VGG model. So as you can see, it will take like 8 more seconds to download. So ideally we should have made a folder here first. The folder should have been named saved underscore model, but never mind, let's run it. It would just not save the model. Okay, there's an error. Okay, let's check. Document called epoch. Okay, I think it had to be epochs. Let's check. Yeah, it's epochs. Okay, so what we'll do, we'll first make this directory called saved underscore model. We do that by mkdir make directory saved model. So now we have the directory here. Now we'll run this again. Let's see how does it run this time. So it's downloading the CIFAR 10 dataset. It will take like 1 minute 20 seconds. So you can actually skip this video by 1 minute 20 seconds or 1 minute 10 seconds. Though it isn't taking that long, it's just showing. So in actual practice, you will be required to train it for like 25-30,000 epochs at least. You'll have to test like for how many epochs it's performing well. Since I'm just showing you, so for demo purpose, I'm just training it for 100 epochs. Okay, so the CIFAR 10 dataset has been downloaded. So it's running. Okay, SRN object has no attribute, disk underscore patch. Okay, let's check. Valid equals to numpy dot ones. Okay. Is it? Okay, we haven't defined disk underscore patch, so we need to define that too. I thought we had defined this patch thing. So where do we define? Optimizer, we build VGG, then dataset name. Okay, so let's define it here. Calculate output shape of T so patch will be integer of self dot high resolution height upon 2 की power 4 2 to the power 4. So the area would decrease by like 16 times, so that is why we have written, because it's, and then self dot disk underscore patch will be equal to patch comma 1. So let's run this again now. Okay, what is the issue now? Okay, loss real images underscore. Okay, while training the discriminator, loss real equals to images underscore hr. Okay, error when checking input exp. Okay, is our data loader class right? Okay, the issue is it had to be images. I am GS. So now let's try running now. And here W will be in quotes. So we are running for 100 epochs with batch size 1 and sample interval as 10. So after every 10 intervals, it will save an image. So it's running. Once it starts the taking 100 epochs, I think it won't take very long. So let's wait, let's see at least the starting part of training. You can like skip the video by 1 minute, I suppose. So as you can see, the training has started. So it will save image after every 10 epochs. So let's make it run for 10 once. Okay. So this one was the low resolution image. So since the training has just started, so let it run for like 100 epochs. After that, the model will be saved and then here, and then you can just download the model. So this is how super resolution in Keras works. Hello and welcome back. So now we will start developing our tool which will take input from the command line. It will take the image address, like which image to work on, and the other input that it will take is whether to perform super resolution or to perform in painting. So we'll be developing that tool using the pre-trained model, using the model that we trained in the previous videos. So after training, I just downloaded those models and save it locally. So we'll be developing that tool in Sublime Text. So let's start coding now. First of all, we'll import the relevant dependencies. We'll import Keras. Then we'll be importing CV2. After that, we'll import NumPy as NP. Then in the end, we'll import sys. So sys is used to take inputs from the command line. So how the process happens is, suppose this is a, okay, I'll just show you once command prompt. Okay, so you can see the command prompt screen. So what happens? Suppose I want to run a particular Python file. For example, I want to run this tool.py. So how I would run that is, I'll type Python, then tool.py, then I'll give my inputs. For example, suppose I want to work on image address, so I'll give it the image address cat.jpg or whatever, or png or whatever. Then suppose I want the other input that I want is in painting, so I'll give that. Suppose I want to give another input that is like some other input, for example I want to give some size, or I want to give number of images. So how that would store is, so what Python would do is, it would store all these in the form of sys.argv. So they'll be stored in the form of list. So the 0th term of that list will be the tool.py, the first term will be cat.jpg, the second term will be inpainting, the third term, the third term would be 34, and so on according to the list. So for us, what we want is, we want the user to enter Python, then the name of our tool, which is tool.py. Then after that, we want our user to enter the image name, that is the image name. And in the end, our user will enter in painting or super resolution. So suppose the user enters super resolution. So what will happen is, this will be stored as sys.argv0, sys.argv1, sys.argv2. So this is how we access these in the Python file. So that is it. You need to know for the command line. So now we can move back to the coding part. So we'll take location as sys.argv1. Then we'll take the task, like what is the task, what does the user want us to do, whether the user wants us to perform in painting or the user wants us to perform super resolution. So that will be taken as sys.argv2. So once we have taken these, so now we'll build two functions. In the first function, we'll build a function for super resolution, which will load the model for super resolution and do the prediction for super resolution. In the second function, we'll build for image in painting, where the function will take an image and perform image in painting. So let's start coding our function for super resolution. So it does not make sense to load both super resolution models and image in painting models here, because suppose if user just wants to do in painting, so there's no point in our Python file to load super resolution model. So even the model loading part we'll be taking in the function. But what we can do is we can actually load the image, because we'll require that. So we'll take an image as image equals to cv2 dot imread location. So this will load our image in. So now let's start writing a function for super resolution. Function to perform super resolution def super resolution, and it will get image as an input. So first of all, the model that we built, that works on 64 by 64 by 3 image. So what we need to do is we need to check whether the image that has been loaded is actually of this size. If it's not of this size, our function needs to resize it to 64 64 64 64 64 3. So we'll check that. If image dot shape is not equal to 64 64 3, so if the image isn't this, then our function will resize the image. So image will be equal to cv2 dot resize image 64 64. So our image will be resized if it isn't of correct size. Now we want to prepare our image to be loaded into the into our model. So we need to perform two tasks. First, we need to load our model, and we also need to prepare our image. For example, our image is currently 64 64 3, so we need to convert it into 1 64 64 3. We also need to perform pre-processing. For example, when we wrote our model, what we fed as, we fed that as a. So when we fed, we made sure that all the numbers in our image were between -1 and 1. But here, all the numbers in image are between 0 and 255. So we need to make sure, we need to convert that into -1 and +1. So we do that by image equals to image upon 127.5. So it was between 0 and 255. Dividing by 127.5 will make sure that it comes between 0 and 2. Now if we subtract 1 from both sides, it will come between -1 and 1 and our task will be solved. So we'll subtract -1 from this. So and now we need to resize our image. Our image is currently of the form 64,64,3. We need to convert it into 1,64,64,3. So we'll do that by image equals to image dot resize. So we'll be resizing our image. So the size will be 1, comma, image dot shape 0, comma, image dot shape 1, comma, image dot shape 2. So now our image is of the shape 1, 0, 1, 64, 64, 3. After this, what we need to do is we need to load a super resolution generator model. Load our super resolution generator model. So we saved two files. One was JSON file and the other was HDF5 file. So we'll be loading a model from JSON. Then we'll be loading our weights from the HDF5 file. So we do that by JSON file equals to open. So what I've done is I have saved both the files and I've saved super resolution file in the super resolution folder. Super res, it is in this folder, and the name of the file is generator 1 comma JSON. Then we need to make sure that we enter R also. Now we need to read our JSON file, so we do that by loaded model JSON equals to JSON file dot read, and now we'll close our JSON file dot close. Now super resolution generator model will be Keras dot models dot model from JSON loaded model JSON. Now after this we need to load our weights in this super resolution model, so we do that by super res gen model. We'll use load underscore weight dot load underscore weights. So weights are stored as HDF5 file, so they are stored in superres folder same, and the name is generator underscore weights 1 dot HDF5. So this has loaded our model also. So now we need to use that model to make predictions. So we'll do that by predicted image will be super res generated model dot predict, and we'll feed in we'll feed in our image. So now pred image will be the final prediction. So that will be in the form of 1 comma its super resolution, so it would be 4 times. So that would be 64 into 4 times image. So that would be 1 comma 64 into 4 comma 64 into 4 into 3. So we need to convert it into height, width, and number of channels. So we'll do that by reshaping our image. So we'll do pred image equals to pred image dot reshape pred image dot shape 1 colon. So that would remove the initial one, that is the number of examples or number of images, and we'll be left with height, width, and the number of channels. Now we need to convert it, the prediction is of the form -1 comma 1, so we need to convert it back into a 0 to 255. So what we'll do is we'll do reverse of this. So first we'll add 1, and after that we'll multiply by 127.5. So that would convert our image into the original form. So we'll do that by convert between 0 and 255. Pred image equals to pred image plus 1, and we'll multiply this by 127.5 into 127.5. Now we also need to make sure that our image, this would have converted our image into float, but we also need to make sure that our image is of type uint8. So we'll change the type also. Pred image equals to pred image dot as type uint8. So this will make sure that the type is right. So in the end we'll save our images. What we'll do is we'll save both our original image and we'll save our predicted super resolution image. So we'll save by cv2.imRight comma image. Okay, and the other image, that is the predicted image, we'll save that to cv2 dot imRight pred image super resolution dot jpg, and the name is pred image. So this will save our image. So our function of defining super resolution is done. So in the next video we'll write the same function for image in painting. Welcome back. So now we'll start working on our next part. So we'll start writing the code for image in painting. Image underscore in painting, and it will get image as input. Function for image in painting. So first of all we'll load our model. We'll be actually loading our generator model. So first of all we'll load a JSON file. So JSON file will be equal to open dot JSON and it will be R. After that, we'll read that file. So loaded model JSON will be equal to JSON file dot read. Then we'll close the JSON file. JSON file dot close. Now it's time to load our weights. Load weights into our model. So before that, we also need to load our model. So we'll do that by inpainting underscore generate a model will be equal to Keras dot models dot model from JSON, model from JSON, and it will be loaded model JSON. Now we'll be loading our weights into a model. So we'll be using that hdf5 file. So in painting in generated model dot load underscore weights in painting backslash generator weights dot hdf5. So now we have loaded our model. So first of all, we'll make a function that will randomly mask our image. Then we'll be using that image to for our in-painting task. We can also do something like mask. We can also, if we want to extend this, we don't want to mask externally. Suppose our image already has something missing and we want to try on that, then we can even achieve that. But instead what we need to do is we'll have to give our inputs, like this part is the one that has to be masked. So we are making it a little. So let's start working. So first of all, we'll give the number of rows our image has. So that is 32. Then the number of columns in our image. So that will be 32. Then we need to give a mask height and a mask width. Mask height is 8. And our mask width is also 8. These parameters are same as the one we wrote when we were actually building the model. So y1 will be equal to numpy so this will select a random integer between 0 and image rows minus mask height and the shape will be image.shape 0. Though so the shape of our image will be the number of training examples, that is 1, then the height, width and the number of channels. So this will actually be 0. Image.shape 0 will actually have a value of 1. So that means we'll be selecting one random integer between 0 and the image rows minus mask height. So that will be y1. So y2 will be y1 plus the mask height. Then x1 will be numpy.random.randint 0 image rows minus mask width. So our image has same number of rows and same columns. So whether we write image rows or makes columns makes no difference. comma image dot shape 0, and similarly x2 will be x1 plus mask width So our masked image, let's make a numpy empty array. So that will be the same as the shape of our image. So it will store our masked image. So its shape will be saved as the shape of image. And then the missing parts, numpy.empty, image.shape 0, comma mask height, comma mask width, comma 3. So this will have the missing parts. So this will have like how many missing parts? So it will be 1 for us. This will have the mask height, the mask width, and the number of channels is 3. So that will store our missing parts. So our masked image will be images 0 dot copy. That is, we'll copy our image y1, y2, x1, x2. These will have values y1 of 0, y2 of 0, x1 of 0, x2 of 0. Then over our missing parts, missing parts 0 will be masked image. So we'll add that part, underscore y1, underscore y2, comma underscore x1, comma underscore x2, and then colon dot copy. So this will make our masked image, the missing part will be copied here. Now what we need to do is we need to make sure that this value is 0 because we are masking this. So masked image this is equal to 0 and masked image 0 will be masked image. In the end we'll return our masked image. So this will be masked images. Missing parts, and then we'll return a y1, y2, etc. y1, y2, x1 and x2. First of all, we need to check what is the size of our image, whether the size is 32, 3 or not. If the size is not 32, 3, then we need to resize it. if image dot shape is not equal to 32 comma 32 comma 3. This is similar to the one we did in super resolution, just that the size was 64 comma 64 comma 3 and here it is 32 comma 32 comma 3. So just that is the difference between these two. So if the size isn't this, then we need to reshape it or resize it. Image will be equal to cv2 dot resize, and we need to resize our image, and the final height and width will be 32 comma 32. So after that, like we did in super resolution, we need the images now of the size 32 comma 32 comma 3, we need to convert it into size 1 comma 32 comma 32 comma 3, and we also need to, it is the values of that image are between 0 and 255. We also need to bring those values down between -1 and +1. So we'll both reshape our image into 132 32 3, and we'll divide by 127.5 and subtract 1. So image 2 will be equal to image dot reshape 1 comma image dot shape 0 comma image dot shape 1 comma image dot shape 2. So now our images of the size 1 comma 32 comma 32 comma 3. So now we'll be normalizing that image, we'll be bringing it down to between -1 and +1. So image 2 will be equal to image 2 by 127.5, which is half of 255. Then we'll subtract 1. Now what we'll do is we'll send that image and get return these values. Then after that we'll be using a model. So masked image, comma missing parts, comma y1 y2 x1 x2 will be equal to mask underscore randomly image 2. Now we'll be using our model to predict. So predict a predicted image will be equal to inpainting underscore gen model inpainting underscore gen model dot predict, and we'll be sending a masked image. Now once we get it written, our predict image will be of the shape 1 comma the height, width, and the number of channels. So we'll reshape it. It's also between -1 and 1, so we'll convert it into 0 and 255. Also it's of type float, we'll convert it to uint8. So we'll do it both for our predicted image, this one, and for our masked image. So let's do it for our predicted image first. So first of all, we'll reshape our image. So it won't be 0 because 0 is 1. So it will be 1, 2, and 3. Now we'll bring it between 0 and 255. So new prediction will be equal to spread image reshape plus 1 into 127.5. Now we'll change the format to uint8. So we'll use as type new pred dot as type uint8. Similarly, we'll do the same for our masked image also. Masked image reshape will be equal to masked images dot reshape masked images dot shape 1 masked images dot shape 2 and masked images dot shape 3. Then masked image 2 will be equal to, that is, now we'll convert between 0 and 255. Masked image reshape plus 1 into 127.5. So in the end we'll convert it into uint8. So if you don't convert it into uint8, when you actually save it, you won't get it proper. So now we have converted it into uint8. So now what we need to do is we need to add a prediction over our original image. But before that, first of all, we'll save our masked image. So we'll do cv2 dot I am right masked image dot jpg comma masked image 2. Now what we need to do is, so now what we'll be doing is, over our masked image we'll be adding a prediction, and we'll be adding that prediction only over that the square of y1 y2 x1 x2. So we'll do that by masked image 2 y1 till y2 comma x1 till x2 comma all the channels, and that, so that value, so before that this value was 0, that is, it was masked. So now it will be our prediction. New print uint. Now we'll save this to cv2.imwrite predicted image in painting.jpg, and that will be masked image 2. So now our function is ready. So what we need to make sure, we need to make a way for our code to know which function to call, whether to call in painting or whether to call our super resolution. So what we'll do is we'll use our task. So this here the user would have entered. So we want here the user to enter in painting or super resolution. So this will decide what to perform. So we'll have a if function, if here, if task is equal to, if task is in painting, then we'll call in painting, otherwise we'll call super resolution. So what we'll do, if task equals to in painting, then print performing in painting on image, and we'll call our in painting function, which is image underscore in painting, and we'll give our image. So our image is img, otherwise if task is super resolution, then it will perform super resolution, then print performing super resolution on image, performing super resolution on image, and now we'll call our super resolution function. So it is super, check the name, underscore res, and we'll give our image. Now what if the user enters some random value, for example in resolution or something like that? So we'll add else. If it's none of these, then print enter the right task please. So it will show this in painting or super resolution. So now we'll save it. So this is ready. In our next video we'll be actually running it live and seeing our results. Welcome back. So in this video we'll be running a tool. So this, as you can see, this is the tool, and we have two folders here. One is in painting, it has the models JSON file and the HDF5 file for our in painting task, and the other is super resolution, it has the files, models. So we'll be running this tool now. So first of all we'll open command prompt. I'll type cmd and that will open a command prompt screen. I'll just show you once. So as you can see, there is a command prompt screen now. Yeah, so this looks better now. So now we'll be actually running that tool. So what we need to type is, first of all, we need to type Python space, then the name of our tool is tool, so the name of our tool is tool.py. Then I have added an image here. As you can see, the name of image is cat sq2. It's a cat square image, so I'll write that cat sq2.jpg. So after that, now we need to tell the tool whether we need to perform the inpainting task or the super resolution task. So first of all, I'll give it command as inpainting. So and I'll press enter. So just give it some time. The tool is running. Okay, so it's performing inpainting on image. So I pressed enter by mistake, so you can ignore that. But yeah, it did perform that inpainting task, and as you can see, now there are two images. One is masked image and the other is inpainting image. So let's see them a bit zoomed out. So here you can see the mask image. So though it's very small because the image size is too small. So here's the mask here, and our inpainting task has almost successfully filled that mask up. Now we'll perform the second task, which is our super resolution task. So I'll give it the command .jpg super resolution. So it performed super resolution, and now you can see this was the original image and it increased its size and it did some super resolution. We haven't trained it for long, so if we trained it for more, the results will be even better. So this is how we make a tool which can perform both inpainting and super resolution. Now suppose a person gives a command which is none of these. For example, I give a random command. So let's see what are the results. So ideally, yeah, so it's right. It is saying enter the right task please in painting or super resolution. So it's our tool is working fine now. It has successfully performed our image in painting and our image super resolution tasks.